Right, now on with vectors and the next few sections, and I've just got a little summary here of where we're heading. So position vectors, resultant vectors, what collinear means, and also then the distance between 2 points in space. We're going to cover all these areas if we can. Okay, so position vectors, that refers to that's a vector that gives the position of a point. So it's a vector that gives the position of a point. All right, so this is familiar in that we're familiar with the XY coordinates, aren't we? And so this is exactly the same. So if we've got a point, maybe down here at 5 minus 2, then the vector of that point, the vector that describes the position of that point, will be 5 minus 2. And if we've got another vector that's at 1, 4, right, then the position vector of that point, position vector, is 1, 4, right, which refers to this vector here, going 1 across and 4 up, and this vector here for 5 minus 2. Now this might be O and A, and this might be B here. So then, what is the that's position vectors? That's it really. Was simply a position of the point on the plane or in the three-dimensional space. If we're looking at a three-dimensional vector situation. Now, what about the resultant vector AB of these position vectors? So that's what we're referring to when resultant vector is the result of two other vectors and what comes of that. So the resultant vector AB, that's going to be AB. So the resultant vector AB will equal, well, what's going on here? So this is OA going that way, 1, 4. This is OB going that way, 5 minus 2. Now how do we get from A to B? Well, we can get there via O and via O and then through B. So we can do that. We can just look at the points and think about it. Well, what's happening from A to B? It's going from 1, 4 to 5 minus 2. So that's surely just going to be 4 across and 6 down. 4 across, 6 down. So there's my resultant vector right there. Resultant vector. Okay, we could also look at it as I was about to say there, with AB going from OA, but it's going AO plus OB. So we could go around that way, and AO is equal to minus OA, and OB is just OB. I've got OB, that's 5 minus 2, and minus OA is minus 1 minus 4. So minus 1 minus 4 plus OB, which is 5 minus 2. And if we put those here, minus 1 plus 5 is 4, minus 4 minus 2 is minus 6. And we've got our resultant vector. And we're going to do a lot more work on that style of resultant vector as we go, just trailing. So I can get from A to B. It's a path along known vectors. So it's just the negative of OA, which is, so it's minus this vector here, plus this vector here going in the same direction, 5 minus 2. Put those together and we just add the numbers. There's the resultant vector. So that's all good. So you can just do it on site if you wish, or you can do it using a path of known vectors to get your resultant vector. Why don't I have a look at collinear and what that means? Collinear means you've got points on the same line. Collinear refers to points that are on the same line. So they lie in a straight line. Collinear points lie in a straight line. Now any 2 points lie in a straight line. So we're really talking about 3 or more points, because it's trivial to suggest there's 2 points. Of course, any 2 points are collinear. That's not of any mathematical interest whatsoever. But 3 points, now we're talking about something interesting, because now that's quite unusual. 3 points lying on the same line. So these points A, B, C, A, B, C, A, B, C, points A, B, C are collinear. Okay, so how do we show that we've got collinear points? Well, let's have a look at, so there's an example on page 413 where we've got 3 unit vectors. Actually, no, we don't. We've got 2 unit vectors. Actually, I'm looking at the wrong question. Sorry. On page 417, we've got I minus 2j plus 3k, I minus 2j plus 3k, that's vector 1, minus 2i plus 3j minus 2k, minus 2i plus 3j minus k, that's vector 2, and 4i minus 5j, 4i minus 5j plus 7k. So these refer to points. This is the point 1, minus 2, 3. This is the point minus 2, 3, minus 1. And this is the point 4, minus 5, 7. Now, that what we're being asked to do is show that these points are collinear. Now, we can do that by really just having a look at a resultant vector from going from one point to the other. So if we go from, if we say that's 1, 2, 3, or ABC, might be better, ABC, then AB will be equal to, what's happening here, 1 to minus 2, it's gone minus 3, hasn't it? Minus 2 to 3 has gone 5, and 3 to minus 1 has gone minus 4. So AB's gone there. Well, so we can either go with AC or BC, doesn't really matter, or CB. What we're looking for is a scalar multiple of this to show that we've got points lying on the same line. So BC will be, let's have a look, minus 2 to 4 is 6, 3 to minus 5 is minus 8, and minus 1 to 7 is 8. Okay, I wondered why this wasn't working. I've copied this out incorrectly. That should be a minus 7 there. So that's I haven't given myself enough room. 4, minus 7, and 7 there. So my BC is actually minus 2 to 4 is a 6, 3 to minus 7 is a minus 10, and minus 1 to 7 is an 8. And you can see that AB, that is minus 2, so it's twice as long in the negative direction. It's minus 2 ABs. Now what does that mean? That means that if I've got an A and a B, that means BC is twice as long but in the other direction. That means that C sits down here, but that it also sits in that straight line between A and B. So that shows that we've got that these points are collinear. And importantly, as they've got a common point, yes, they're parallel, and but they go through the same point, which means that they have to lie on the same line. So the important thing here is just to create some resultant vectors to, in fact, with a common point, and show that they're parallel. So parallel is, just think about that. If I've got A, B here, and then I come up with a BC, now my BC has to include B, and if it's parallel to AB, so I've already got this, if I make a C and it's parallel to this, then it's got to lie on that line, doesn't it? So that means that ABC are collinear, which is so what we've done here. So therefore, ABC collinear as AB and BC are parallel. Right, they differ by a scalar multiple, which in this case is here, minus 2. They're collinear as AB and BC are parallel, and B is common. and that's what's important, because if you've just got A, B, and C, D, let's say two completely unrelated points, then all you're doing is proving that you've got parallel vectors. It doesn't mean that A, B, C, D are collinear. But if you go A, B, B, C, or B, D, then B lines up with that, and you've got collinear. So anyway, hopefully that point has been made. Okay, last thing I wanted to look at is the distance between 2 points in space. Actually, I might make a different, or is it a quick lesson, that one? Distance between 2 points in space. I think we can make it fairly quick if we've got, and we're looking at in space here. So if we've got 2 points, and I'll use the same. If A is equal to x1, y1, z1, right? So that's a point in space. Then OA being x1i plus y1j plus z1k, and if we've got B equaling x2, y2, z2 as a point in space, then my position vector OB is x2i plus y2i plus z2k, so that's a j there. Then we have, if we want to now work out the distance, therefore distance AB, so the distance between those two points will be equal to, just as in 2 dimensions we know that that AB itself is equal to the difference between x2, x1. All right, then we've got the distance AB will be, or if you like that, will be the square root, just as in 2 dimensions, it's x2 minus x1 squared plus y2 minus 1 squared. Then it's exactly the same here, but we are including our third dimension of z2 minus z1 squared. So we can go through there and do some examples. I won't put those down here because I've run for 12 minutes already, but we're now okay to get through exercise 12C, 12D, and 12E. So we'll get on with that when I see you next.